Today we begin calculus by looking at tangents and the derivative. Now let's start by examining this graph here and then look at how we can use it to deduct some information. Now we've got a graph here showing change in temperature over time. So let's put a story to it. Let's say we've taken a bottle of water out of a very cold fridge that's at 0 degrees and it's a 40-degree day. So over time that bottle of water is going to go from 0 degrees to levelling out at around about 40 degrees. So on the x-axis we've got time from 0 here to 80 minutes, and on the y-axis we've got temperature in degrees. A little bit of a dodgy scale. It's not perfect, but you get the idea. So we've got a gentle curve here showing the change in temperature over time. It looks like there's quite rapid change in the beginning when the bottle first is taken out of the fridge, which sort of levels out after a while. It takes a while to come all the way to room temperature. Now, some things that we need to learn how to draw on charts like this so that we can take information from it. A chord is any line that joins two other points. So think of it like a chord, like a bowstring almost. So if I was to say put a chord on this from say 0 to, obviously I'd get a ruler, I haven't got one on me. Let's join one from say this point to this point. I've drawn a chord and it's straight. Now, a secant is very much the same thing, except it just continues out either end. So if I was to continue that line out further, one way or the other way, or both, I've now drawn a secant. So it's something that really cuts through the graph and it hits it in two places. Now, a tangent is a little bit different. A tangent touches the curve just once. So if you're going to draw a tangent, you take your ruler, and the idea is you can place it anywhere along the curve and actually draw a straight line that just hits that curve once. So if I was to draw a tangent, say here, I'm effectively getting a straight line that just touches at one point. I could also draw a tangent here. Oops, that's a bit dodgy because I don't have a ruler on me. Or I could draw a tangent up here. You get the idea, that one's a lot flatter. You could even have a tangent right down here at 0, a straight line that only goes through the curve once. So what do tangents and secants or chords help us to do? I'm going to class these two together because really whether or not they continue on the other side of the curve or not, for our purposes it doesn't matter. Well, let's have a look. If we look at the gradient of a chord or a secant, let's have a look at this gradient here, for example. The first one that we drew. That will show us the average change in x compared to y. Now here we've got time comparing to degrees. So if I wanted to look at what the average change was that had occurred over that first 60 minutes, I could say, well, over the first 60 minutes we went from 0 degrees to, let's say, 35 degrees. So I could say we've changed 35 degrees in every 60 minutes. And I could convert that down to how many degrees per minute we've had as a change, couldn't I? I could say it's 35/60ths of a degree per minute. And of course I can easily divide top and bottom here by 5 and say it is 7/12ths of a degree per minute. That's the average change that's occurred over this time. Now, was it changing steadily? It wasn't, was it? We've got a curve here which shows it was changing quite rapidly and then it really levelled off. So this average change doesn't really give me the full picture of what was happening each minute because we weren't losing exactly 7/12ths of a degree every single minute, were we? So here is the crux of what we do with tangents and why we love to use them in maths. A tangent's gradient gives us really important information about a curve. It tells us how steep the curve is at any one time. Let's have a look at this tangent here. If I can work out the gradient of that, then I know the gradient of the curve right there on that point. And of course, on every single point of this curve, there's a slightly different gradient, isn't there? The gradient starts off quite steep, and it gradually gets less and less and less steep. So the gradient's changing all the time. So the tangent's gradient actually gives us the instantaneous change right at a particular one point. And that's a really important concept. Now, what do we call this gradient? Well, it's got a special name. It's called the derivative. And we are going to start, it's got a few different notations, but the first one we're going to learn is this. We call this f dash x. Now it looks a lot like f of x, doesn't it? Well, we say f dash x is the gradient of the tangent to any function, let's call our function y equals f of x, at any point on the curve. Okay, let's have a look at an example. Now, I've drawn up a bit of grid paper here on the board. It's not been measured though, so it's not exact, and I've drawn a graph freehand. Now, our example says graph f of x equals x squared, same thing as y equals x squared, and estimate the gradient of the tangent to the curve, so the tangent is that line that just touches the curve, at these points, x equals 0, 1, 2, and 3. Now, I've only drawn the right-hand arm of this parabola because I'm only investigating these points, but clearly I could have drawn the entire parabola and had it going up the other side like that. Now, can I afterwards graph y equals f dash x? Because f dash x will be a function in its own right, as we'll see. All right, first we've got to draw some tangents to our curve. So I'm going to take my ruler and actually draw a tangent where x equals 0, 1, 2, and 3. All right, the first one's simple. This tangent is just going to be horizontal because obviously when x equals 0, that's the turning point of the curve. So a tangent that just touches there is going to be completely flat. So I can see the gradient of that one is 0. Okay, let's draw a tangent where x equals 1 now. Now to do this, put your ruler where x equals 1 on the curve, and then see if you can just rule up a line that just touches the curve at that one point. Now, to look at the gradient of this line, let's line it up and see what the rise over run is. I'm going to count from here to here and say that's 4 over 2, which is the same as 2 over 1, so that looks to me like a gradient of 2. If we could draw a tangent where x equals 2, put your ruler on the line, on the curve, and draw up a line. That's a steeper line now, isn't it? Now, if I want to measure the gradient of that, I'm going to go up to somewhere where it looks like it's going through a box. It's roughly 4 boxes across and 4 boxes high and 1 across. It's 4 over 1. That's a gradient of 4. And if I look at the gradient up here, it's much steeper, isn't it? I need to draw in something that looks roughly like this. Now, this is much steeper. This will be a gradient of around about 1, 2, 3, 4, 5, 6 boxes down and 1 across. So we've got a gradient of around about 6. Now, I was estimating there, but I can see clearly that there's a pattern. Now, what's going on here? What do I need to do to the x to turn it into f of x, f dash x? Well, it seems to be doubling, doesn't it? And what that tells us is that f dash x is just 2 lots of whatever x is. So as the curve gets steeper, I can expect this to continue. Now, if I wanted to graph the derivative, which is the second part of the question, this is exactly the same as graphing y and x, and graphing y equals 2x, which I know is a line that looks something like this with a gradient of 2 going through the origin. But instead, we're not graphing y, are we? We're graphing f dash x, so we can easily change our y's here to f dash x, and we're graphing literally the same thing. And this is the derivative function of this original function.